Hello, good afternoon. This is week 8, starting today on Monday. And we're going to go back to physics part of the course with all the same rules. That is to say, there will be this recorded video presentation, and then there will be a synchronous meeting on Monday at 3:20 at the usual time for this course. Everybody can log on. It'll be a WebEx meeting, and ask any questions, or I'll discuss this material again and any extensions of it or suggestions or whatnot. And then you'll have your laboratory sessions with your laboratory TA. And for example, asking any questions, or how do I do this and it doesn't work, and so on, and maybe your TA can demonstrate for you, and so on. And also the Critical Friends group. I hope that some of you find that useful, actually, in these isolated times, to be able to talk to other students rather than just simply listening to me on a screen. So this is week 8, and it's on measuring charge and current. Now, this is maybe the first time in which we measure things that you don't see, like measuring charge, for example. You don't see charge. Sometimes you feel it with a static electricity, or for maybe lightning, for example, is actually movement of charge. But we'll be building electroscopes and excuse me, and so on. Now, we won't be doing much with current because we've done current before with solar panels, but it's not possible to have 6 solar panels at home right now. So we have them in the lab and so on. But so I'll show you some photographs and talk about current a little bit. So, what is charge? Well, you can easily get a supply of electrons by just rubbing them off of atoms, and that's called static electricity. Okay? So if you rub your hands together, actually there's some charge on your hands. And you know that if you walk across a rug in the winter with, say, leather shoes and a synthetic rug, you can get a spark. I mean, you touch the door handle, you feel a spark, and that's actually static electricity. You really rubbed a lot of electrons off of a lot of atoms, and you've accumulated some charge. So that's what we're going to do. Okay? Now, as I mentioned, we usually get the currents and voltages from solar cells, which are effectively like batteries. And so I left in this old photograph, actually, of an Air Force base in Nevada. And you can see, as far as your eye can see down here, there are banks of solar panels, okay? And okay. So here is, this is a more recent photograph of installing solar panels on the roofs of buildings. And so, in fact, I only put this up here because, for example, we've used solar panels, and unfortunately online we won't be able to do. But in fact, the price of these solar panels is down to like $1 a piece, and each piece is about 8 square inches or something like that. Okay, and the price per kilowatt hour is continuing to fall, and as the efficiency of solar panels improves, the price will fall even more. So it's something to keep your eye on. Okay. Now, when you discuss electricity, static electricity, or even currents, there's 2 major classes of materials. Okay, almost all materials fall into one or the other class. There are conductors and insulators. So, you know what an atom is? An atom is a very tiny nucleus. Very tiny nucleus here, surrounded by electrons swirling around. And the electron is actually held on here by not very much energy at all. It's only a few electron volts. So in conductors, the electrons are free to move completely throughout the conductor. So all metals are conductors. The best conductor of all is gold. The next one is silver, and behind that is copper. Copper is much cheaper than silver or gold, and so all buildings are wired with copper. Okay, it's an excellent conductor, by the way. And so in a metal, the electrons are like a fluid that moves freely throughout the metal. Okay, now it's actually interesting. Let me make a side story about conductors. Benjamin Franklin wrote a treatise on electricity in 1750. Now, 1750 was 25 years, a little more, before the American Revolution. Okay, and he became well known actually in the Royal Society in London, which was, of course, the mother country. We were only a colony. London was the mother country. And he was actually quite well known as a very good scientist who understood electricity. And so Franklin had in his mind the notion that this fluid, this stuff that was actually static electricity, was somehow a fluid. The fluid flowed in metals but didn't flow in other things, for example, like wood. Okay, and so he had the wrong theory. But basically, functionally, his theory was correct, because electrons do act like a fluid, and they move throughout metals and so on. So what are insulators? In an insulator, you can have individual electrons attach themselves to an atom of the insulator, and the electron will stay put. It's kind of fixed on that atom, and it doesn't move around to other atoms. Okay? And the absence of an electron on a region, on an atom and so on, is equivalent to a positive charge, and that positive charge also stays put. So if you put charge on an insulator, it simply stays where it is. If you put charge on a conductor, it'll just move freely wherever it needs to move. Okay? So in fact, insulators are actually used to protect us from, for example, conductors that have voltages on them, for example. So those are the important things. And so you must understand this difference between the two, because otherwise you'll be very confused when you start to do any kind of work with static electricity or with currents. So here are some examples of static charge. It's kind of what we'll be doing. I just downloaded these. Here, for example, the upper left, you can get static electricity by rubbing. So, for example, the orange colored thing is actually a plastic strip, and this is a cloth. The red thing is a cloth. And you rub the cloth over the plastic strip, and what you find is that the plastic becomes negatively charged. In other words, and the cloth is positive. So what happened is the electrons, by rubbing atoms against each other, you physically rubbed off electrons which preferred to go into the plastic. So the plastic, the orange plastic, becomes negatively charged, and those electrons kind of sit on the surface of the plastic everywhere. Okay, and that's in fact exactly what we're going to do. Now, in the lower panel, there are clouds, and so clouds are kind of collections of water molecules and so on, and there's also friction as the cloud moves, as the wind blows a cloud along. There's friction between the cloud and the surrounding air, and you can separate charges. You can actually do the same thing. Electrons can be rubbed off of atoms of nitrogen and oxygen, or even water molecules and so on. And then dramatically, when you get a lot of charge, for example, a lot of negative charge at the bottom of a cloud, and when that gets close to the surface of the Earth, there can be a lightning strike. A lightning strike is actually all of those electrons burrowing a path through the air of the atmosphere and going into the Earth here, right? And you can also have lightning between clouds. If one cloud is positive and one is negative, you can get a bolt of lightning, which is actually the electrons going from one cloud over to the other cloud. So that's static charge. Now, how do you get static charge? Well, on the right-hand column, right-hand side here, is a so-called triboelectric series. There are a lot of things listed here, common things. Your hands, leather, maybe rabbit fur, glass, human hair. All the way down in the middle there's wood, and you keep going down and there's a styrene, saran wrap, and near the bottom there's PVC, polypropylene vinyl, PVC, also silicon and Teflon. At the top it's labeled as positive, at the bottom it's labeled as being more negative. And so the way you generate charge is you take any two different objects, for example. We're going to take, for example, wool or maybe paper, okay, and PVC. So in your box there's a PVC pipe, 8 inches or so, and if you rub the PVC with paper, or if you like with wool, works even slightly better, because they're better because they're further apart on in the triboelectric series. Then the PVC will become negatively charged because electrons will come from the paper onto the PVC pipe, and the paper or wool will be left positively charged because they've given up their electrons to the PVC. Okay. Now this is basically driven by the fact that the atomic states, you know that last time, I mean, atoms have energy levels, and so there are a lot of quantum states, and you can have an empty energy level, and that empty energy level can accept an electron from outside, either from higher up in the same atom or from outside. The electron can come in. So the atomic energy levels on the materials, the atoms and the molecules of these materials at the bottom have a lower energy than the materials, the atomic energy levels of the molecules and so on in the top. So electrons prefer to find themselves at a lower energy state. It lowers the energy of the whole system and it's more stable, etc. So that's the fundamental driving fact behind the triboelectric series. In fact, I recently saw an article, a research problem. It's actually extremely complicated. Understanding the triboelectric series is extremely complicated because it involves many different kinds of molecules and molecular bondings and so on that compete with each other. But in the simple main, that's it. And all you need to know is what this. If you do any two of these things, for example, you can do glass and silk. Okay. Now both of them are up at the positive half, but in fact the glass will become more positive and the silk will become negative. Okay, because that's the order they have in the triboelectric series. Okay. So now suppose you rub two things together. Now, for example, here's take balloons. You can blow. There's balloons in your kit. You can blow up a couple of balloons, and rub the balloons with, for example, your hair. Okay, rub it in your hair or with wool or cloth. Okay, and the balloon being a rubber will become negative. Generally speaking, it'll become negative. And then if you hang two balloons, in fact, I didn't do this, but you can do it if you like. With hang the two balloons from a thread, maybe from your 1-foot ruler or something. Hang them down, and then charge them both negative, and then they should repel each other, because that's the basic law, force law for charges, is that like charges repel. Okay, so negative repels from negative. Positive repels from positive, and negative and opposites attract. So negative and positive attract. And that's the force law. That's it. There's a formula for it, but we don't need the formula. This force law is called Coulomb's law. And with a little bit of effort, actually, we could actually measure this force, okay? It gets a little awkward because you put charge on here, but you don't quite know how much charge you have, really, and so on. And it's a big object. It's not a small object. So, in any case. So this is the, you can do this. Now this I got from Wikipedia. You look at, do a search for Wikipedia. Tribo means to rub in Greek, so you're rubbing two surfaces together. This is maybe, it looks like animal abuse, but maybe it's not. Actually, here's the cat. And styrofoam, all right? So the cat's fur is positively charged, and all the styrofoams are negatively charged, and there's a very strong attractive force between the negative and the positive charges. This is what is called static cling for your clothes. So you pull a wool sweater off over a cotton or maybe whatever, another something else further down in the triboelectric series. You get static cling, and it's the same thing with rubber shoes, leather rubber shoes on a rug. Now this is more prominent in the winter time, and we'll get to that. Why do you notice static charge in the winter, but not so much in the summer? And we'll get to that, okay, later on. So here is a static charge here. I'm going to play this. This is a little bits of paper cut up here, and here is the PVC, 8 inches of PVC in your kit, and here's some colored paper cut into centimeter pieces and cut into smaller pieces, and with some scissors. So let's play this. Okay, here's another electrostatic. It's not exactly electroscope here, But what we have is, for example, some colored paper, which we can cut up into little squares and some smaller squares. And here's our PVC again. We're going to use this piece of aluminum foil as a ground. So I want to roll this PVC across here to get all the charge off of it onto the copper, onto the aluminum foil here. I do that because after you've charged up a bunch of things, your table is charged, you're charged, the pen is charged, there's a bunch of charge everywhere. So an electrostatic experiment gets to be complicated if there's just too much charge around. So I want to have a decent ground. I would discharge this. So now notice that there's kind of no effect here. I mean, I will go over the top of these small cut up squares of light paper. Nothing here. So now let's charge it up. Here's again a paper towel. I charge this up. I get a good charge on it. And then you can see, okay, it just picks them up like this. All right. And now some of them are, see, some of them are being pushed away, and that's because the little paper squares pick up negative charge and the PVC is negative. So now the papers are being pushed away from it, electrostatically repelled. So a couple of them pushed away. And falling off now because the charge is draining away from the PVC. And now what you've seen, however, dramatically, is that the electrical force was much stronger than gravity. Gravity is pulling everything down to the table, but the electrical force overwhelmed gravity, just picked them up like that, okay? So the electrical force is in fact much, much stronger than gravity when you just strip it down. But you can see the dramatic effect right here. Okay, now you can cut up small paper, colorful paper, light paper. It's better if it's tissue paper. Even tissue paper works better because it's lighter. But you know, you can also, let me discharge the PVC again. See, it's discharged. Just take anything like again, just shreds of paper like this. This is just again a paper towel, shreds of paper towel, fairly even big pieces. Put them here, and then charge this up. You see, it picks them right up like that. Okay. Okay. And they're being, yeah. So there's a lot of charge here. Still a lot of charge. Okay. Holding them, picking them up. So it's a very strong force. Now, the charge is actually, we can't tell it right away, but it's slowly leaking away here. That's because there's a little moisture in the air. And later on in the recorded video, you'll see why water in the air will discharge static electrons on the surface of anything. Okay.
Okay, so here's a commercial electroscope. It costs about $50. In elementary school, it would be worth to buy one of these things for your science classroom. But an electroscope is a way of basically measuring charge, or actually doing a decent job of measuring charge. What it has are metallic leaves that hang down loosely. Okay, so on the left-hand side here, there's one metallic leaf that hangs down, and then the conductor goes up, and there's this ball on the top. And there's inside of this little glass box. You can take the glass sides off and get inside, okay? It's meant to prevent any, wind currents or whatever not. This is actually a gold foil on the inside. So you touch, so on the middle picture, I guess, I touch the top of it with a PVC tube, okay? And put some charge on it. And then you can see that the gold leaf has flipped up to the right hand, has flipped up to the right hand side, okay? I mean, it has, in other words, you put some negative charge here. All of this becomes negatively charged. So this is negatively charged. The gold leaf is negatively charged. And the gold leaf now is being repelled because they're like charges being repelled, and you can see it angling up like this. Now, you can also put it on its side, for example, do the same thing. Here's the PVC pipe that's touching the top, okay? And you can see the gold leaf just stands up vertically, okay? And basically it beats gravity, no problem, okay? So now this is a commercial electroscope, and it's nice to have, okay, but you can actually make your own. And so here's making your own electroscope. Here's a small video for that.
Hello, this is a simple electroscope, which you can make and should make, actually. It's a classic electroscope, and we'll make 3 or 4 different kinds of electroscopes. But these are one way of measuring charge. And so the early people, Coulomb and so on, even Benjamin Franklin did experiments like this. The idea here is that there's a this is copper, so it's a conductor, and it's wound around. There's a lot of winding at the top, and then at the bottom and down here, there are a couple of aluminum strips. I just punched a little hole in the aluminum strip and then hung them on the end of the copper wire. And maybe you can use tweezers if you want to. And now this is just being held here, and I actually using the styrofoam block that's actually in your week 14 folder. You can just go pick it out and use it. And I'm just using it as a way. I just punched the copper wire through here so it has mounted and so on, and I taped it down so it doesn't fall over. We'll use this styrofoam block again when we make motors, electric motors. So now, this is all the copper is conducting and the aluminum is conducting. So now, and there's no charge here, so both aluminum leaves are just hanging down. And I used a thin aluminum, but I mean, if you have heavy-duty foil, it'll work also. So I just used a pair of scissors to cut them into 2 strips and then punched a hole in them. So now, this is PVC, which you can buy at a hardware store. And I just cut them into 8-foot lengths. And if you look at the triboelectric chart, which is right here, you'll see that it's a list of materials. At the very bottom, near the very bottom, is the PVC. And at the top are things like, for example, paper or wool or fabric or fur, animal fur. And if you pick 2 things very far apart, one at the very top, one at the very bottom, and rub them together, excuse me, what happens is that, for example, here's just a paper towel and a PVC. If you rub them together like this, give them a good rubbing like this, then the electrons jump from the paper onto the PVC. So the surface of the PVC is actually covered with free electrons. So it's negatively charged. And this is left over as being positively charged. So literally, we've rubbed electrons off of atoms. Now, the reason why they do it is actually very complicated. In fact, it's a subject of research for some people. It has a lot to do with the molecular attraction of these atoms compared to those atoms. And in the end, the atoms here, the molecules here have lower energy levels. Okay, well, you know, atoms have energy levels in them. And so the electrons prefer to jump from here over to here because they go down to a lower energy state. That's basically the reason why. So let's see what happens now. So now you can pick any 2 things off the triboelectric series you want. Here's a fabric and here's a paper towel. So here we go. Let's charge it up, make sure it's nicely charged again. And I'll bring it close to the copper wire without touching the copper. And you see that the aluminum, I haven't touched anything. The aluminum strips spread apart from each other. I move away, they fall back again. I move close, they go apart again. So this is by induction. Literally, the negative charge on the PVC has taken the electrons inside the copper wire and pushed them down to the bottom. The electrons have literally gone to the other end of the copper wire to avoid being repelled by the negative electrons on the PVC. And they go down, and then when they're sitting there on the aluminum strips are now both negatively charged, so they push apart. So let's do that again. Let me just push them closer together. Okay, so now there's no charge here. It looks like there's no charge. They're hanging directly down. This time, just for fun, I'll use the fabric. Okay, here's the fabric. Give it a good rub. There's a certain, okay. And you don't have to go very long, but just a little bit. Come close again, and they go far apart. Fall back again. Now what has happened here? Now you see there's a little bit of charge here. I'll go down again and I'll touch, actually. I'll come into contact. So some of the electrons from here actually jumped
onto the copper. Okay, now these two things are pushing them apart. There's still some charge on here, so if I come close, you see I affect them, all right? Okay, so now there's some residual charge on here, and if I touch it, then any extra charge on the copper wire and the aluminum strips will go into me. So I go like this, and now you see they both just drop down. There's no charge on here. So by touching it with my finger, I'm acting like what is called an electrical ground. So on every electrical appliance, every plug-in, there are 3 prongs. 2 prongs carry the voltage, and 1 prong is ground. And the big prong is ground, and it's literally connected to a water pipe into the ground, which means that any charge you put on that ground plug will go right into the ground, okay? And it'll disappear. So if you want to discharge anything connected to the ground. Now, it works very effectively because the earth is huge. The earth will accept any amount of charge you give it and never change its voltage at all. I'm not the earth, of course, but I'm much larger than this piece of copper. So I serve as an electrical ground to this piece of copper. So let's do that again. Let's charge it up again. It looks like everything is discharged here now. And I'll go right up and I'll touch it. So I'll transfer some charge to the copper wire here. Okay, so I've transferred some charge to it. Okay. Well, yeah, I want to have them far apart. So if I touch them, they'll probably discharge again. I want them to be kind of... There you go. I charge them up. Transfer some charge here. They're pushing apart a little bit, but they've now separated. That's not you can see it's not a very good one. But now they're charged up, and I'll touch it, and they should discharge. They discharge, just drop down. So that's a simple electroscope, and we'll do another 2 or 3 of them. Thank you.
Okay, so here's a soda can electroscope. As you can see, it's just sitting on a styrofoam cup, and the can is a conductor, so that's like the large coiled copper, and then you can hang over it aluminum, silver, or gold strips. Now, I found this one difficult to make. I tried to make this one, but I found it difficult to make, and the problem was I was just using aluminum, and the 2 strips hanging down, they have to be separate strips, okay? If you have one piece of aluminum that's just bent over, then the two sides of the aluminum are connected together, and they don't push apart very easily, okay? So that doesn't work very well. But I did manage to take 2 separate strips of aluminum, and I hooked them over here, and then it kind of worked as an electroscope. But it wasn't very satisfactory to me. So now, so let's go. We saw this on the electroscope, but didn't point it out at the time. Here's charging by induction. And so there's 4 panels here, 1, 2, 3, 4. And number 1, first panel, there's a metal. This could be like this, for example, could be the soda can. It's just drawn this way as an oval. This is a soda can. And then you bring in a rod, like, for example, our PVC rod, which is negatively charged. You bring it close in. On panel 2, you bring it close in. What literally happens is the negative charges on the PVC repel the electrons in the metal. The electrons really go to the other side. They go to the other side, leaving the near side positive. So now, at this point, you can do a little quick trick. You can touch on the panel 3. You touch the left-hand side with a ground. For example, it could just be your finger. Just momentarily touch it with your finger. It drains off the negative charge, leaving the positive charge there. Then you move the PVC rod away, and you then have a soda can, which is positively charged. Okay? So that's one way of getting a positively charged object when you started out with a negative PVC charge. Okay? That's called charging by induction. Now, you should try this. You can try it with a soda can. You won't be able to know that you have a positive charge there, though. But you can maybe appreciate the skill of somebody like Coulomb, who measured the forces between these charges, and Ben Franklin, who also did similar electrostatic experiments. You can appreciate the difficulty of doing these. So in any case, now let's go to the next panel here. Here's, take a soda can again, same soda can would be fine. And then you charge up a balloon. Now you can charge up a balloon, for example, just by rubbing it with a cloth, for example, or wool, okay? And then the surface of the balloon becomes charged, and you can bring it up next to a soda can, and you can see what happens. Instead of a balloon, you can just use the PVC pipe the PVC tube that you already have, and charge it up with paper towels, for example. So here then is what it looks like when you do that here. Let me get this over here.
0. Well, this would be a demonstration again of an electrical force. What we have here is a pop can, okay, and aluminum, very light aluminum, and I'll discharge it to make sure, I'll discharge to ground to make sure there's no charge on this. Then here's our same old PVC tube again. Now, what I'm going to do is I'll charge up the PVC tube. Let me discharge it now, PVC tube. And when I put it close to the can, the negative charge on here will drive all the electrons inside the aluminum, drive the electrons to the other side. So this charged side of the aluminum can will become negatively charged, leaving the front face positively charged. So the positive charge on the front face and the negative two will attract. There'll be an attractive force here. And the negative charge here and here will be a repulsive force. But the positive charge here will have a greater force because it's closer. It's not as far away. This negative charge is farther away and the force is lower. So there should be the force on the front face going this direction is bigger than the force of repulsion on the back. So that the aluminum can should move in this direction. And there's a force on it. So the force means it'll accelerate. Now, when we get to Galileo, a couple of weeks from now, we'll understand how a force makes a mass accelerate. It's F equals ma, actually, one of Newton's laws. So let's just do the experiment now. Without actually understanding what we're doing, we'll do the experiment. So here we go. I'm going to charge up our PVC tube again. Give it a nice charge. Again, the aluminum can is neutral. There's no charge on it. Okay. There you go. And so the aluminum can was attracted. In fact, it was even accelerated. Okay. If I were to keep it a constant distance away so that the force was constant, then it would accelerate at a constant rate. So let's do that again. Okay. Now, it's hard to measure accelerations, but when we do, look at the acceleration as a result of force, we can put a meter stick here, a ruler, and take a slow motion video. And with a little work, we can actually measure the acceleration of this mass. And the acceleration times the mass of this is going to be equal to the electrical force. So you can actually measure a force due to electric charge, okay? Which is what Coulomb did when he studied this, okay? And also I might say Benjamin Franklin played a very large role in electrostatics in the year 1750, which was 25 years before the Declaration of Independence. Benjamin Franklin was quite good at doing experiments like this. I find them actually truly rather difficult to do, but I want you to do them as good practice, and it's something, again, that children can do this, okay? So it's like, shall we say that this is, in some sense, it's like magic. You don't touch anything, but it starts to move. So how did that happen? That's like magic, right? What it really is electricity. Okay, so we'll continue then with discussing this in the lecture.
Let me just add to that, to the accelerating a soda can. In a classroom, you could have a contest. Who can get their soda can to go the length of the table fastest? Okay, have a race. Have a soda can race. And you get to have your PVC tube, and you get to put all the charge on it you want to, and so on. So there's a certain amount of skill. You want to get the PVC charged PVC tube as close to the can as possible, but you don't touch it because it'll discharge, and so on. So it could be an interesting competition in a classroom. Okay, now another manifestation of this force is you can actually bend water. I mean, water from a faucet. You can charge up a balloon, And you can see that the balloon will attract the stream of water as shown here in this photograph. See, water is also a conductor. It's a conductor because they're ions, they're salts. Usually, any tap water has salts dissolved in it, and so the water actually is a conductor. And the conduction part, the charge carrying particles in water are not electrons, but they're ions. But they move slower, but they're still conducting. All right. So you can also use the PVC pipe here, for example. You don't have to use a charged balloon. I think the PVC rod is really much easier to use than a balloon, but you can try them both. Children should try them both. So here is a small video of this is just in my kitchen
sink. Here's a stream of water just from the kitchen sink. It's a smooth stream of water. And now water is actually a conductor because all water has salts in them, various salts, maybe sodium chloride, and the ions from the salts make the water conducting. So you can actually send a current through there. But because it acts like a conductor, the electrons or the ions in there will actually respond to an electrical force. For example, the charge on our PVC tube, I'm charging it up now. I'm charging up our PVC, and I'll bring it up next to the stream of water here. And you see it bends it. Okay, it moves over some to the other side. Okay. Okay. I'll maybe charge it up a little bit more. But you see the stream of water is attracted to the charged PVC pipe. And I'll explain to you, I'll show a picture. See, I'm deflecting an inch or so, by the way, at the bottom. Okay. Okay. And what it does, it actually pushes the negative charges to the other side, and the positive charges are on the PVC side, and so the net attraction is towards the PVC. Okay. All right.
So here's a kind of picture of where the charges are. The balloon is negative. The surface of the balloon has negative charges on it. And then the stream of water has ions inside of it. And the positive ions are pulled to the right, and the negative ions are pushed to the left. And again, the same thing with the soda can is that the attractive force, which is the positive charge being attracted to the negative charge of the balloon, that force is slightly larger than the repulsive force of the negative balloon and the negative charges on the other side of the water stream. So, so it's surprising actually that you can even see this force because the water stream is not very wide. Okay, it's only a quarter inch or an eighth of an inch or something wide. So in any case, these are all manifestations of the force, and it's all a way, if you like, to measure charge. Now, I was going to do demonstrations of other electroscopes, which didn't work out very well for me. Let me actually go back. Let me say, here we are on slide 17. Let me go back to an electroscope here. And this one, so yeah, let me go to here. There's in your envelope for this week, there's actually in the bottom right-hand corner of your envelope is a gold foil. It's about, I don't know, 1.5 inches on a side, square foil. This is a gold foil, and you can use the gold foil instead of aluminum foil. Works much better. But gold foil is extremely difficult to use. Excuse me. Gold foil almost floats in the air. It's so light. This is very, very thin gold foil, and it'll hang over the copper wire. It'll hang over the copper wire almost like a wet rag. Okay. And so I challenge you to use the gold foil. It's actually rather difficult to use. You need a pair of scissors. It's in between two pieces of paper here, so you can actually use a pair of scissors to cut the strips, and then maybe use tweezers maybe to handle the gold foil and so on. You're welcome to try that, but it's very challenging. All right. So let's go back to here. So we were here. Now, finally, let's see, on static charge, there's a difference in between winter and summer, and with as far as doing electrostatic experiments are concerned. So, for example, in the summer, generally speaking, the humidity is high. High humidity means there are a lot of water molecules in the air. Now, the water molecules are a small fraction of the total air, but that means there are enough water molecules to really see a difference when you're doing. Now, the water molecule is H2O, which means 2 hydrogen atoms and 1 oxygen atom. Now, it turns out, well, the water molecule, let me state as I stay here on the top left-hand side, is that it's really a wonderful molecule. It's the basis for life on Earth. And it's a remarkable molecule in many respects. And it is what's called a polar molecule. That is to say, you cannot see the hydrogens, the 2 hydrogen atoms like to give up or donate each of them donate their electron to the oxygen atom. In other words, the oxygen atom has an energy level a little lower than the energy level in hydrogen, and so they spend a small fraction of their time twirling around the oxygen molecule. So the oxygen end of the water molecule is negatively charged, and the hydrogen end is positively charged. Now, this is called a polar molecule. Okay, it has a name. It's called a polar molecule, and so therefore it can orient itself. When you put a charge nearby, it'll affect the water molecule. So let's take on the middle. There are 3 panels, 1, 2, and 3. So in the top panel, there's this green surface, which is, we've charged it up negative. So this could, for example, be a PVC, a piece of PVC or some piece of plastic, and we charge it up negative. So, and then in the air, there are a bunch of water molecules just banging around, and the water molecules actually travel pretty fast, okay? They're 1,000 feet per second, actually, before they bump into something. But in any case, there are a bunch of random water molecules in the air. Now, in the second panel, number 2, the water molecules will orient themselves such that their positive end, which is the hydrogen end, the positive end is pointing in the direction of the negative wall because it attracts. So the water molecule then, here's the wall. The wall is here. And I'll do it the other way around here. No, I'll do it this way. No, I'll do it this way. So here's the negative wall, and the water molecule orients itself around so that the hydrogen end, the positive end, points towards the wall. And then, so the positive is slightly closer than the negative end, and so the water molecule gets an attractive force towards the wall. So you can see the 3 water molecules are all oriented that way, and the first one that gets to the wall, it gets close to the wall, and an electron jumps across from the wall. An electron on the surface of the PVC jumps over to one of the hydrogen atoms. It just jumps. Ends up inside the hydrogen atom. So then on the bottom frame, the water molecule, this one particular water molecule, has a negative charge of -1 electron. And because the whole water molecule is negatively charged and the wall is negatively charged, that one molecule is driven away from the wall. It's repelled by the negative wall, and it just shoots out. And then you can see then the next water molecule comes in. It comes in close. It's down on the bottom. And an electron will jump over onto that one. It'll flip around and get driven away. And molecule by molecule, electron by electron, these water molecules will take away all the charges on this surface and completely discharge the surface. Okay? So if you do this experiment, the PVC pipe and so on during the summertime, you'll have to do it quickly. Be careful because your surface will discharge very quickly. Okay. Whereas in the wintertime, when there are no water molecules in the air, then you can put a surface charge, static charge, on the surface of something, or put it on a metal or a PVC pipe, and it'll stay there for a long time. Okay. So that's the reason why you notice you walk across the rug, then you touch a doorknob and you get a shock, and you get a shock during this winter when there's no water molecules in the air, but during the summer it won't happen. Okay, now another couple of slides here. One more slide here about static charge. There are many industrial uses of static charge. Upper right-hand corner, there's a kind of old. This is not an inkjet, but this is a static charge copy machine. What you do is you make an image, static charge image, put a piece of paper there, and then the negative charge toner, which is like graphite, are electrostatically attracted to the paper as the drum rolls around, and then the paper comes off, and you have a black image. This is a black and white copy machine here. Okay, and the black gets embedded in the paper by electrostatic attraction. Another one I find interesting is painting cars. Lower left-hand corner, you have a car. It's metal, and you attach the positive terminal of a car battery to the car, so the car now becomes positively charged, and then the negative end of the 12-volt car battery, attach it to the nozzle of the paint nozzle. So as you spray paint out of the nozzle, the modules of paint droplets, microscopic paint droplets, are negatively charged. So guess what? You spray it out, and the negatively charged paint droplets are attracted to the car. In other words, they don't end up on the ceiling or the walls. They end up on the car because they're attracted to the car. The negative charges are attracted to the positive car. There's another beautiful consequence of this. For example, suppose you get a region of paint on the car in which you have too many negative charges there, okay? Then other negative charges in will avoid that spot, and they'll go to a spot which is more positive. And so the layer of paint on the car becomes extremely uniform, becomes very smooth. So almost automatically you solve 2 or 3 problems right away with car painting when you do this electrostatic trick. Finally, in the lower right-hand corner, it's a smokestack, and you have you're burning coal down here, for example. So there's a lot of soot that's coming up, a lot of carbon particles, large and small, and so on. And then you put across the bottom here this blue dotted structure, which is a grid. It's a negatively charged metal grid. So you put a negative terminal of your battery there. And so the soot particles that come up and go through this grid, it could be a mesh, for example, a wire mesh, go through here, they become negatively charged. And so then as they continue up the smokestack, you have a couple of red plates which are positively charged. And so the negatively charged soot particles are attracted to the red positive plates, and they're dropped into a bucket and so on. And so the smoke particles going out here, well, there are very few smoke particles going out because you take them all out by this electrostatic force, and the only thing that goes up is hot air rather than pieces of soot and so on. So this is called a scrubber as a name. Most power plants have this. I mean, it's kind of required by the Environmental Protection Agency, which keeps soot and smoke particles out of the air. Okay. All right. So that's electrostatic. So it's fun to do these things, and it's maybe challenging for 2nd or 3rd grade, but 4th, 5th, and 6th graders should have some fun making measuring forces with electroscopes and so on. Okay, now I'm going to briefly go through current, for example, which we won't do much with. Okay, I mean, it wasn't possible to put solar panels in your boxes, and could have put batteries and light bulbs and things like that. But in any case, let me just talk about them a little bit. Current is the movement of electrons in wires, for example. Well, actually, in truth, the soda can, when we brought up the PVC pipe to a soda can, there was actually a current inside of the soda can. The electrons went to the other side. That's actually an electrical current. Very brief electrical current, very small, but still it was a current. So here's a collection of batteries here, for example, all the way on the right to a little tiny small battery used maybe in hearing aids, I'm not sure, through various sizes, AAA, AA, and all the way up to a rather high current. Now, all of these batteries have the same voltage, like 1.5 volts, for example, or if you gang them together, you get 6 volts or 9 volts and so on. But they have, the big one on the left has a higher current capacity, it has more total stored energy, it'll deliver more current for longer, okay? Now, at the bottom is a so-called DC or direct current circuit. So on the left you have a battery, an ordinary battery, could be a AA battery. The top end is so-called positive or high potential, and the bottom end is negative or low potential. Okay, and then you have a wire that goes from the positive terminal through a switch, goes to a light bulb, and then goes through the filaments of the light bulb, and then goes on to here a buzzer. Okay, and then goes through the buzzer and back to the bottom end of the negative end of the battery. Now this is called a circuit. It's called a complete circuit, because you go from the top, you go from the positive terminal all the way through whatever you want to go through, light bulbs, motors, whatever you want, and it goes back to the, returns back to the battery, the negative terminal of the battery. That's called a complete circuit. And when you do that, the light bulb will light up and the buzzer will go, the motor will go. Okay, there's a switch here. If you open the switch, then there's no longer a circuit, and no current flows if you open the switch. So when you go into your room and you turn the light switch on, that's what you're doing. You're actually completing the circuit so that the current flows and the light turns on. Okay. Now here's a solar panel. You can buy these like $1 a piece. If you shine light on the solar panel, the top becomes negative and the bottom is positive, and that's how the electrons move on the inside and so on. So if you take one of these panels, shine a light on it, you'll get like half a volt. Okay, it's like a battery with half a volt, and depending on the light level, you can have typically a 1 amp of current, 1 ampere. Okay, so it acts like a battery. And then the battery, just you can take the solar panels just like batteries, you can add them up. The top configuration of 4 batteries is adding batteries in series, which means you go from low potential to high potential, then you go from low potential to high potential on the next battery, and you keep adding them up. What happens now is that across all 4 batteries, each battery is 1.5 volts, like a AA battery, say. You'll have a total of 6 volts, okay, and a current capacity of 1 amp. That's called in series. So you can actually you can add up the voltages for a bunch of batteries by adding them up, by connecting them in series. If you connect them in parallel, that's called parallel at the bottom, you connect all the high potentials to one terminal and connect all the low potentials to another terminal. Now the potential difference across these 4 is 1.5 volts, okay? But the current capacity is now 4 amps instead of 1 amps. So that's the series and parallel configurations. So now here is one of these solar panels. You can see it's the raw solar panels. There's nothing connected to it. But you shine light on it and put a voltmeter on, you just measure voltage, right? Simple as that. And here's a lesson that we learned painfully, is that these solar panels are extremely fragile. They break apart. Okay, so we managed in panels 3 and 4, we would encase them in plastic and protect them and so on. So someday maybe if you come by next semester or next fall, come by 102 lab, I'll be glad to take you into the lab and show you, let you play with solar panels and so on. But what we did after we making a bunch of these, you take, in this figure, for example, you take 6 solar panels and you connect them in series. So each solar panel is half a volt, so 6 panels would be a total of 3 volts, and quite a lot of amperage too, by the way. And then you can connect that across the motor that has a wheel on it, and the motor goes and the wheel starts to turn. You shine light on it, the wheel turns. You take the light off, the wheel stops. Okay, so we would then have little project boards like this, and you'd put a lot of solar panels on there and hook them up, and put the wheel, a wheel or 2 there, and then you have a little electric car. Well, it's not a very elegant car, but it actually does run. Okay, and so and this is just inside the classroom itself here, but on a sunny day you can go outside. This happens to be a class during the winter time. You can see the boots that the students are wearing. So we had a lamp. We shine a lamp on it and it goes, right? So, okay, so that's current and solar panels. Now, for this week, in your lab sessions with your TAs, I'd like you to consult the triboelectric chart. These are activities you can do. Consult the triboelectric chart, choose 2 materials, and and use the PVC pipe and paper towels, work very well. Okay, then make your own electroscope using 2 aluminum foil pieces hanging from a copper wire or from a paper clip. If you use a paper clip, you just have to be careful, because modern paper clips have they're plastic coated. Okay, you don't want plastic coated. You want them to be metallic. Okay, on the outside. Then I challenge you. And if you can manage to do this in your video, I would be overjoyed. And you try to improve this design with gold foil. You'll have to be very careful. Scissors and tweezers, okay? And if you can make a electroscope with the gold foil, that's a really big win for you, okay? So then also pick up pieces of paper. For example, you use different size weights of paper, for example, and you can compare the electric force to gravity. So gravity is mg, that always points down, and then the electric force points up, for example. And you can see that the electric force is bigger than the gravity force because you can just pick it right up, okay? Now, I'd also do the soda can, okay? And estimate the electric force from the acceleration of the aluminum can. Now, this you can't really do unless you already know about forces of motion. We're going to study motion due to forces later on, and maybe measure accelerations, which is what Galileo did, for example. He measured accelerations. And that's a little hard to do, honestly. I mean, you can look at the video, and you have to have a slow motion video and a meter stick and so on. But those are things you can actually do in a classroom someday. Not easy to do. Okay, so thank you very much, and I'll see you Monday at 3:20 in the afternoon for a synchronous session. We go over all this, ask questions. I could pull out toys from. I have the same box you have here, so I can do things. You can ask questions. Why doesn't this work, and so on. Okay, thank you, and see you later.